So the FFT algorithm given by Cooley-Tukey gives a maximum number of complex multiplications equal to n log 2n. Whereas if you do blindly the original DFT as is written by summation, we agreed that the number will be equal to n square.
So it will be log of 2, sir? Log to the base 2? It will be log to the base 2?
Which one?
Will this be log to the base 2?
Because 2 to the power of p, na? So we are only talking about p. P is nothing but log of n. I should put 2 here. So the reduction in this complex multiplications will decrease exponentially, right? Because if n goes to some 10,000 or something, and then this will be 1 million versus what? 10,000 is what? 1000 is 10 bit, and another 10, maybe another 3 bit. So 13, 14 bits will correspond to 10,000. So 14 into 10,000 versus 140,000 versus 10 to the power of 8. So that is the kind of reduction in the number of computations that you need to do if the number of samples grow larger and larger. And this is the beauty of the Cooley-Tukey algorithm. And if you just look at very critically, what all he has done is to use the principle that w to the power of n plus k is equal to w to the power of k. That has simplified the whole thing because of the cyclic property of the e to the power of j function. That he has very intelligently done it by reshuffling this way of doing it. Now, if you have 8, for example, what will you do? Next one is 8. What will you do? Look at it into 4, 4. And 4, you know this butterfly. So you do the same butterfly for 4, 4 and do them, add them up by another matrix multiplication, diagonal matrix multiplication. So higher order can be slowly brought down to a lower order 2 by 2. This is 2 by, actually 4 by 4. This, if you look at this 4 by 4, what is basically is this, right? Is a 2 repetition of this. So basically 2 by 2 operation. So you bring down the 2 to the power of p operation to gradually by decreasing by 2 at every time, at every stage of operation, and finally come to a 2 by 2 operation. So for any number, as long as 2 to the power of p, the same technique can be adopted to bring it down to the smallest one, which is 2 by 2. So this is what is known, and also imagine that this is a kind of a, this operation is a repetitive operation, right? As you go down from there to there, similar operation going on repeating at every stage. So the basic operation gets go on repeated. So when you write the software for this, it becomes so easy to write down that operation in a repetitive manner. So people have written the FFT software, and now FFT is considered to be a test now for the speed of a computer. If you want to buy a computer and want to test that computer speed, one of the problems which is used for testing is to see how much time it took to do an FFT of so much size. And that gives you the well-defined figure, how much it should be, and you check whether really the operating time of the computer or the one complex multiplication operation is as is claimed by him. So it becomes a standard test. Okay. So this is about the way you find out the spectrum of a signal given in the sample format of a time signal which is band limited and also time limited. And time limited may appear to be very restrictive, but don't think it is restrictive, because in the world there is nothing called infinite time. Your experiment can be conducted over a finite time, your observations can be taken over a finite time. There is nothing like a doing something on infinite length of time, right? How you observe a earthquake over a period of time, you observe the human body over a period of time, or anything you do has a time limitation. You can't go on doing it infinity. So time limitation is not really a restriction as you are making it out to be, because that's what the real world is. And bandwidth limitation is also not a restriction, a restrictive assumption, and because there is and nature doesn't permit things to change at very fast rate to have a very large bandwidth. So the finally there is a finite bandwidth for every signal. So because of that bandwidth limitation and time limitation, both of them simultaneously is not an unreasonable assumption. And once you have them, you have finite number of samples, and once you have finite number of samples, you have finite number of sampled frequencies given by the capitals. And that can be obtained by the simple algorithm, which is the Cooley-Tukey algorithm. Did I give the word in the previous class or not? Cooley-Tukey. It's C-O-O. There is no dash here, but I always read dash. Two gentlemen, Cooley and Tukey. And Tukey has spent all his lifetime in finding spectrum of signals in Bell Laboratories, very famous man, and analog signals, good old days in speech signals. But he and he together worked out this algorithm in 1960. It became a very popular algorithm. In the laboratory, when you go there, you have a button there. You just press the button, it gives you FFT. So there is a software into the computer. You can take 1000 points, and it takes the Fourier transform of that by using FFT software built into the computer itself, the oscilloscope itself as a software package. Now, one is to write a software for this and put in a computer. The software operates on this 1000 samples or whatever the number of samples and gives you a number. But then you can see still the computer will take some time, analog to operations, and each operation computer will take 1 cycle time or 10 cycle time or some number of cycle time. So it takes some amount of time, and in real time sometimes it may not be workable. What do you mean by real time? I am getting a sample, I am getting another sample, some operation I have to do on the previous sample before the next sample comes to me. The time available between the sample is the sampling time. Within the sampling time, you may not be able to do this analog to operations on a software. So people have built hardware which will do these operations, which they call firmware, as you people know. When you do some software package, translate into hardware, it is called a firmware. So you use a firmware chip which will contain some amount of software, hardware and software, which will do the operation much faster than the computer. So they are also available to do the FFT. But this is something which is now become a household word, because everybody needs to know spectrum. Any domain you go to work with, machine analysis, volcanoes or earthquakes or health of the body or river flow or structural stability or anything you do, you need to do a spectrum. And hence this has become so universal and so extensively used by every discipline, physics, chemistry, so on. Once this Cooley-Tukey algorithm came, chemists converted the spectroscope, IR spectroscope, into an FFT spectroscope, fast Fourier transform spectroscopy in IR band. So now everybody has started using the FFT. So that completes my exposure to exposition to discrete signals. We went from analog signal and we we've given some various methods of doing various mathematical operations on the analog signal by using hardware, mostly by using operational amplifiers, differentiation, integration, multiplication, addition, all the mathematical operations I could translate one to one into an equivalent, mostly approximate, but almost as good as the original mathematical operation by using operational amplifiers. Then we went into discrete version and found the same hardware will do the operations on the discrete also, except when it came to spectral analysis. There we used a heterodyning or a band pass parallel bank of band pass filters in the analog domain. In the digital domain, the only method that's available to me is, one of the methods available is simply the FFT, either in hardware or in software. But the algorithm is same whether do it in hardware wise or software wise. Then the last domain we are left with is the digital domain, right? So now the sample values which are discrete in time but continuous in amplitude, right? Samples you can take any amplitude from minus into plus infinity, but they occur at discrete times. Then we studied in the very beginning of the course that we would like to say that this amplitude is not a continuum, but remains within some bound, some voltage, and this voltage is quantized, and each quantum level we will put it into a binary notation and convert this amplitude into an equivalent set of binary numbers. Larger the number of bits you take, more closely you can approximate the sample amplitude. Theoretically, if n is infinity, p is equal to infinity, you have 2 to the power of infinity number of possibilities of the levels. So, you can cover almost any continuum of values. But p, if it is infinity, is meaningless. So, p will be some finite value you choose. So, you have so many levels of quantization, and as a result of that, there is an approximation between the original analog value and the approximated value. And as a result of that, there is some amount of error between the actual sample and the approximated sample. And we agreed in the first class, in the earlier classes, that the error is called a quantization error, and this comes out to be equal to, delta square by 12, right? I gave you that formula, quantization error. So, the smaller the delta, the quantization error becomes small. Smaller the error means number of samples number of bits becomes larger and larger. So, you choose the n depending upon how much error you tolerate, and then quantize it to that many number of levels. So, now how do I converted them into binary format. How do I convert? I am giving a continuous number, I need to convert into a set of binary numbers. So, this is what we call as analog to digital conversion, ADC, analog to digital conversion. And once you do that, you do the operation in the digital domain, addition, subtraction, multiplication, whatever is there. And I am sure you must have been exposed to this digital, some exposure on gates in your physics course, I think in class 12 or something. But we'll spend a bit more time on that. And once those operations are done in digital domain or binary in binary domain, you end up into set of binary numbers. You will have to convert them back to analog numbers. So, I need to have a way of doing DAC also, inverse operation, analog to digital and digital to analog. So, we will study the ADC and DAC, DAC in the coming one lecture. Then we will go into how to do this digital domain operations, okay, so called multiplication, so called addition and so on and so forth using gates.